So now we have this expression for n, which is essentially gv over lambda t, f of 3/2 plus z, the plus denoting that we are looking at a bosonic system, n0 z. So as usual, the fugacity has to be determined from this relation. But if we look at this as this function f of m eta of z was 1 over m minus 1 factorial 0 to infinity dx x to the power m minus 1 z inverse e to the power beta minus eta. I think we did make an error while we sorry, this has to be minus of eta for a specific eta. If it was plus, then I know that this is just going to be fm plus of z is just going to be minus of 1 beta epsilon. Terribly sorry for the mistake. This has to be e to the power x minus 1. Now this is a very complicated function, and usually its representation in terms of simple functions are not possible. But we do know the high temperature expansion of this. The high temperature expansion of Fm so in a high temperature expansion gives us Fm plus of z was 1 over m minus 1 factorial. This was already taken care of. It was simply sum over k equal to 1 to infinity z to the power k, k to the power m for z greater than equal to 0, less than equal to 1. One should note that if I set z equal to 1, so Fm plus of z equal to 1 becomes sum over k equal to 1 to infinity 1 over k to the power m, and this is zeta of m, where the zeta function is the Riemann zeta function. The series converges for m greater than 1 and f plus m of z tends to infinity for m less than 1 as z tends to 1. So series converges for m greater than 1 and f plus m goes to infinity if m is less than equal to 1 as z tends to 1. On the other hand, f plus m of z is finite for all m greater than 1 and for z greater than equal to 0, less than equal to 1. So coming back to this, then I have coming back to this expression for the particle number is f of 3/2 plus of z plus g z 1 minus z. The first term that you see over here is the number of particles which is contained in the excited states, and this is the number of particles which are contained in the ground state n equal to 0. So this is the term, the first term is the term which is contained, which essentially represents the particles contained in the states other than the ground state. But now we have clearly seen that this term is limited by this function, right? And for a Bose gas, I know that the maximum value of Z can happen. There is a limit on values of Z, that is Z can be greater than equal to 0 or it must be less than equal to 1. So clearly when Z approaches 1, then this part, the first term, we will write down this as n epsilon maximum. There is a maximum number of particles which you can accommodate in these excited states, and that number is given by GV over lambda t zeta 3 half, where zeta 3 half is approximately 2.612. Now, this is a very important inference. You see from the expression for the total number of particles in your system that you can accommodate only a certain number of particles in the excited states. There is a limit, upper bound on that. So if you keep on adding particles to the system, you're going to hit this limit. And then if you keep on adding more and more particles, where do they go? They go to the ground state. And that is when your condensation starts to appear. Sorry, not the condensation, starts to happen, and the condensate starts to appear. This goes as V t to the power 3 half. On the other hand, so the second term, this is the term, N0 can be ignored if Z is very, very less than 1. So if you're not hitting the limit of Z to 1. On the other hand, if N, the total particle number, is dominated by the number of particles in the ground state, so that you have Nz is approximately this, you see what happens to Z. This implies that Z is approximately N over N plus, not approximately but exactly N by N plus G. G is a tiny number compared to N, which is 10 to the power 23 typically, and therefore you see this value is 1. So whenever this condition is satisfied, that you actually see that the number of particles in the ground state start dominating the total number of particles in the system, so most of the particles have gone into the ground state, then you have actually hit the limit Z equal to 1. So in the thermodynamic limit, we rewrite this equation which we had over here, and a little up. So we had the expression N was equal to N epsilon plus N0. We rewrite this equation as 1 is equal to N epsilon over N plus N0 over N. Clearly, if N0 is not sufficiently large so that you have not hit the Z to 1 limit, then in the thermodynamic limit, you can ignore this term and most of the particles are accommodated in the excited states. In contrast, whenever you have populated all the excited levels, there's a limit, this epsilon max you have reached, you start populating the ground state, and that's when if Z is equal to 1 and N epsilon is equal to N epsilon max, then you have populated all your excited energy levels, and then essentially N0 is given by, you have hit the limit of Z to 1 as Z is equal to 1, so you see the N0 diverges. So essentially the number of particles in the ground state is given by total number of particles minus N epsilon max, right? So we conclude therefore that n epsilon over n is equal to 1 for z less than 1 and 1 is equal to n epsilon by over n plus n0 over n for z is equal to 1. Therefore, we can see that when the total particle number is less than n epsilon max, which is GV over lambda t times zeta 3/2, or we can rewrite this condition as n lambda t over GV is less than zeta of 3/2. That means you can still accommodate the particles in the excited levels, so that you have this expression for n, and the fugacity must be determined from this expression, as we have done it for a fermion system, for an ideal Fermi gas. Now, in contrast, when n is greater than n epsilon max, which is, let's GV over lambda t zeta 3/2, or n lambda t over GV is greater than zeta of 3/2, then you have hit the limit in putting particles in the excited states. Therefore, in that case, your n0 is given by n minus n epsilon max, which is n minus GV over lambda t zeta 3/2. This means that there is a condition at which point the condensate can appear. I can figure out a temperature. So I can clearly see that based on this, the condensate starts to appear when n is GV over lambda t zeta to the power 3/2. That means when your number of particles in the system has hit the upper bound, upper limit of n, of the number of particles you can put in the excited levels. The condition when condensate starts to appear. Again, at this point, I would like to iterate that, look, even though we are talking about a condensation, and whenever one talks about a condensation, one talks about visualizes a condensation in a real space, it is not really a condensation in a real space. It's actually a condensation in a momentum space. All particles, so whatever you have been talking about is labeled by this momentum vector k. The single particle levels are labeled by the momentum vector k. So what is actually happening is you are actually populating the state with the zero momentum. So if you can visualize the momentum space, then you are going to see a peak which is starting to appear in the zero momentum state, and that is exactly what people have seen in experiments. So this essentially means that for large enough temperatures, you have sufficiently large amount of thermal energy to excite the particles in the excited states, so that they are in the excited states. But as you keep on decreasing the temperature, as the temperature comes down, the density becomes high, or either you could have the temperature coming down, become smaller and smaller, or the density is raised, which means you keep on adding particles and particles until you hit this criteria. What essentially happens is the positive correlation between the bosons ensures that they go and, because they are attractive, so they go and sit at the ground state energy epsilon equal to 0. So defining x equal to n lambda t over gv, then the fugacity is defined by z is equal to 1 if x is greater than zeta of 3/2, and solution of x is equal to f plus 3/2 z. So fugacity, something is wrong here, fugacity is equal to 1 if x is greater than zeta 3/2, and or is the solution of this when x is less than zeta to the power 3/2. Recall the first leading order correction to this function f 3/2 of z. f 3/2 goes as z for small enough z, so that you have the solution x equal to z. If you want to plot the fugacity, so this hits a value 1 whenever your x is greater than zeta 3/2, but for small enough you'll have z is equal to x. Not really, so not drawn to schematics, so let's just quickly draw it first. For small enough I'm going to have, and you expect that the curve becomes something like this way. So let's shift it a little bit to the right so that we can see that this is going to be your zeta 3/2 and not this. So this is how your curve should look. The condition for condensation to appear is given by x equal to zeta 3/2, right, which is n lambda t over gv is going to be zeta of 3/2. So now lambda t is beta h square over 2m pi raised to the power half, so that the thermal de Broglie volume is beta h square over 2m pi raised to the power 3/2. So then n over gv 1 over zeta 3/2 is equal to 1 by beta h square twice m pi raised to the power 3/2. So capital N by V is a small n, the number density, g zeta 3/2 raised to the power 2/3. I have 1 over twice m pi, which is going to be your kb tc. So we will replace the beta here by beta c, indicating that this gives me the temperature. So you have a critical temperature Kb of Tc, which is given by 1 over 2m pi n over g times zeta of 3/2 raised to the power 2 by 3. I am missing out a factor of h square, so that this has to be h square in the denominator. So this is the critical temperature that you are looking at. At this temperature, your condensation starts to happen and you starts to see a condensate that appears at the k equal to 0 momentum state. Now, the particle number in the excited state n epsilon over n is equal to 1 for t greater than Tc, because all the particles that you put in essentially goes into the excited states if you are away from this critical temperature. But the moment you hit the critical temperature, you essentially hit a limit of Gv over lambda t zeta 3/2, so that this n epsilon goes as t to the power Vt to the power 3/2. And you clearly see that from this condition that we had, that this gives me the temperature at which the condensate starts to appear. So I can sort of write down this as lambda Tc Gv is equal to zeta 3/2, so that lambda Tc is equal to Gv over n zeta 3/2, right? Or essentially I can write down Gv over n, and if I look over here, then Gv over zeta times zeta 3/2 divided by n, which is n epsilon over n, is Gv lambda t n zeta of 3/2, which is essentially lambda Tc over lambda t. So this is therefore T over Tc raised to the power 3/2. So this is T over Tc raised to the power 3/2 for T less than Tc. So as you start hitting the critical temperature, you start to get this. Now, the number of particles in the ground state is 0 for T greater than Tc. However, as you cross the critical temperature, then this becomes 1 minus T over Tc raised to the power 3 by 2. And this expression follows from the fact that 1 plus 1 is equal to n epsilon by n plus n0 over n. So that n0 over n is 1 minus n epsilon over n. If you carefully study these two expressions, one can plot them also. You see that as you approach 0 and 0 temperature, the number of this thing vanishes, so that I have this is my Tc. Let's say we'll draw a vertical line, and let's say this is 1, then this is going to be n epsilon over n, number of particles in the excited states for T greater than Tc, and this goes as this T over Tc raised to the power 3/2. For temperatures higher than Tc, the occupation in the ground state energy level is 0, and as you start Going below the critical temperature, the occupation in the brown state starts to increase, going as T to the power 3 by 2, so that 1 minus T over Tc raised to the power 3 by 2, and so that you have the plot which looks something like this. So that this is 1 minus T over Tc raised to the power 3 half.